Welcome back to ECE 441A, 541A. Homework number 1 could be due today. If you want to turn it in, it's due Sunday. There's 3 different ways you can turn in your homework assignment. One is to give me a hard copy here. Another is to put it in my ECE mailbox, and you can do that maybe as late as Sunday afternoon. You can do it even later if you make your homework assignment a PDF and upload it into the Dropbox, and then you have until 11:59 on Sunday. Those are your 3 options for submitting homework. I guess you could hand it to me during office hours this morning after class sometime. Exam number 1, as a reminder, is in 2 weeks. So we may have a fuller class in 2 weeks, would be my guess. We don't have quite as many students attending in person during the normal classes, maybe because I'm making it too easy for them not to be here, but I'll have to check to see if they're actually watching the videos to give them credit for attendance. Today what I want to do, and there is practice material on D2L for exam number 1 if you want to get ready with your weekends. You've got 2 weekends before the exam. Today what I want to do is finish up our connection of these 4 different representations. You've heard of 2 sides of the same coin. Well, these representations are the same side of a pyramid. We have a pyramid structure, and you're just looking at that system from 4 different ways or from 4 different representations, and I want you to be comfortable going back and forth between those representations. Then we will develop the equations of motion for a DC motor, which is an electromechanical system where we're coupling electrical and mechanical systems together, or subsystems, to form one moving object driven by an electrical voltage. Then we will have a quiz. It'll be a linearization quiz. We'll try to get linear, or we'll see if you can identify what makes a system of equations linear or not. We probably won't get into the linearization process, but this tells you where we're headed. We'll talk about linearizing a system if it is nonlinear, and then we will start talking about doing system identification, coming up with the equations, a transfer function for a system based on physical measurements or from a step response. So you hit the system with a step and you watch and see how it behaves, and you can now extract the information you need to create a transfer function from that piece or pieces of information, and that's what you're doing in lab number 1. Here are the different connections. This is a busy diagram, but I want us to be able to see these 4 different ways of representing a system and interconnecting or getting back and forth between these different representations. Last time we started with a state space representation. We moved into a block diagram via the all-integrator block diagram approach. Then we went and we found the transfer function from Mason's gain. I think what I'll do today is I'll find it a different way. I'll do it mechanically using the Cheer 1 approach to go from state space to transfer function, which is the C SI minus A inverse B plus D, and we'll hopefully verify that we obtain the same transfer function either going from block diagram to transfer function or from state space to transfer function. And today I want to finish up all 4 sides and move from a transfer function into differential equations, and that's really just a process of cross multiplication. It's pretty straightforward once you have a transfer function to find a differential equation that allows you to model the way the system dynamics are interrelated based on the inputs and outputs of that system. Since it's Friday, let's do a cheer. There's Cheer 1. We're going to go from state space to transfer function. which says that we're now going to use this formula or this expression, G, the transfer function, is the output matrix times SI minus A inverse times the input matrix plus, if we had a direct connection between the input and the output, that would be our D matrix. And I've simply inserted, I'm going to go through this quickly because I don't want to spend a lot of time. We're just trying to verify that we can get to the same place going different ways. And this is by starting with a state space representation and getting to a transfer function. The first line is simply introducing the necessary matrices. The next line is forming the inverse, and for a 2 by 2, there's sort of an easy way to approach it. You just interchange the diagonal entries and you change the sign of the off diagonals and divide by the determinant, which I'm labeling as this delta. And that's just a scalar polynomial, the determinant in this case. The determinant is the product of the diagonals, entries, or elements minus the product of the off diagonal, and that's what I'm showing as delta there, and I'm explicitly showing minus 2 times 0 so that you don't, in general, forget that you have to consider those off diagonal terms if they're both non-zero in the determination of that determinant. But in this case, you can see that if you found the roots of your determinant, where are those roots? They're the values of S that cause those expressions to vanish, or that expression to vanish, and one is S equal minus 1, the other one is S equal minus 3, and those in fact were the eigenvalues that were on the diagonal of our original system matrix. They were at minus 1 and minus 3, and so we do have consistency, which is good. Those are the poles of our system. They're at minus 1 and minus 3. Is the system stable? Open loop. Yes, because we have negative real parts on those eigenvalues or on those poles. And in this class, what we will be worried about is if our system is not stable, or if we don't like where those poles are, we want to be able to change those pole locations with feedback. Here, we're just going to look at, or we are just looking at, the open loop behavior or dynamics. Now that 1 over delta is a scalar. I can slide that wherever I want in this expression, and it might be easier to perform one of the multiplications versus another. I have two matrix multiplications. I have a row times a 2 by 2, and I have a 2 by 2 times a column. But if I look at the column, the B matrix, the input matrix, how many non-zero elements do I have? Or do I have any all zero rows in that column? Yes. So really that B matrix is just pulling off the last column in that 2 by 2 matrix that it's multiplying. It will just pick up, if you did the row times column, it's only going to retain or keep the last column in that 2 by 2 matrix when you multiply the 2 by 2 times the input matrix B, which gives us then the input or the output matrix 4, 5 times 2 as the 1, 1 entry in that leftover column, and the 2, 1 entry is S plus 1. Doing the multiplication of those two row and column vectors gives us then what we had, I think, last time, which is a numerator of 5s plus 13, and our denominator, once we've multiplied it out, as s squared plus 4s plus 3. And that should be consistent with what we derived from Mason's gain formula for this same system. That was really just a quick aside. I simply wanted to connect those up, and I didn't want to spend a lot of time. Now what we want to do in this picture of these 4 different ways of representing a system, we want to move from the lower right transfer function to the lower left differential equation. And what I say to make that connection is to simply do cross multiplication. By that I'm meaning our transfer function g of s is just the ratio of our output y over the input u. If we now cross multiply or clear the fractions, or I'm sorry, clear the denominators in both sides, I'm multiplying both sides by the determinant on the, or the denominator on the right, and I'm multiplying both sides of the expression by u of s, which is the denominator on the left. And this now allows me to obtain an equation in the frequency domain. And the only thing you have to recall or remind yourself of is what happens when we multiply an expression by s in the frequency domain. What does that correspond to in the time domain? It's a derivative. And in this case, then, we have y differentiated twice because of the s squared. Then we have it differentiated once, scaled by 4, and then we don't have it differentiated but scaled by 3. Meaning this frequency domain blue equation now becomes, in the time domain, y double prime plus 4y prime plus 3y, and on the right we have the input and its scaled derivatives, or 5u prime of t plus 13 u of t. And that's the same system that we started with in a state space representation. It's now written as a second order differential equation. And it just gives you a different way of thinking. If you really like differential equations, maybe you like to see your system this way. If you like state space representations, maybe you like to see it that way. If you like a transfer function, you can look at it that way. The state space can quickly go to the block diagram, and you can now see it in an all-integrator block diagram form. That now allows us to complete this interconnected block, or 4 different ways of representing the same system. And if we wanted to, we could now take this differential equation and put it into an all-integrator block diagram form by isolating the highest derivative and start. How many integrals would we need, or integrators would we need? 2. And now we may have to be a little bit more careful when we do this, because we don't want to just be integrating the input by itself. Well, we'll maybe talk about that later. But you can get by with 2 integrations in this particular block diagram of solving this second order differential equation. Let's now move into an electromechanical system. Pardon? No, we've already done the block diagram for that system, and now I was suggesting you could now go from that differential equation to a block diagram, but we're not going to do that. I thought you would have fun doing that tonight. It's Friday, right? Not only will you cheer, you'll stand up and do those cheers, cheer 1 and cheer 2, but then you'll start pulling out your block diagrams and trading those with your friends, transfer function, state space, having all sorts of fun. Here's the DC motor, and there's actually many different ways of configuring a DC motor, but we are looking at number 6 in table 2.4 in the 13th edition. Maybe a different table, maybe a different page number in other editions of the book, but this one is an armature-controlled DC motor versus having to control it via the field. And the way that we will introduce any excitation in the motor with the field is by means of a permanent magnet. We don't need to know what that necessarily means, but it's nice to kind of have an idea, but it's coming to us indirectly, that information, via the schematic. And what we're doing now is we're really just creating a system that we can now apply a voltage to. The armature circuit, it's a bunch of wires, so it has some resistance, and they're coiled wires, so it actually has some inductance. We'll label this as R sub A for the armature resistance and L sub A as the inductance in the armature. And then we have what turns out to be a controlled voltage source, V sub B, which is impacted or influenced by the speed of the mechanical shaft that's attached to this rotor of your motor. And I'll schematically show that. There's my load, or my shaft, on my motor, and the motor shaft, maybe I'm accounting for its angle, or maybe I will at some point account for its speed, the time rate of change of that angle theta. But when we apply a voltage, that actually imposes a torque, which I will label as tau sub m, on that motor shaft, and that's enough, hopefully, to spin the motor. What we want to do is find a transfer function that relates the input, the armature voltage, which in the frequency domain we might label as capital V of S. And how is that then related via this transfer function to the output, theta of t, which is the angle of the motor's shaft. We will actually model this via two subsystems. We have our electrical side. Obviously, you can write a KVL equation for that circuit. And then we will have the mechanical side, which is no longer translational. You're good with masses and springs and dashpots. Now we want to do the same thing for rotational inertia. Instead of translational systems, we now have rotational systems. But again, that's a mechanical system, and they're coupled by this essentially dependent voltage source that occurs because of that shaft spinning in this magnetic field. So let's look at the electrical side first, and I hope that you can just sort of memorize what we have there in terms of the circuit, because it's going to disappear as I scroll up. On the electrical side, if we do Kirchhoff's voltage law, we can now see that we have minus V of t. Starting in the lower left, we're just going to go into the negative terminal of our voltage. We have minus V of F, and let me go ahead and introduce a current in that armature circuit. Let me call that I sub A. And now what's the voltage dropped across that resistor? Ohm's law, right? And Yes, thank you. R sub A, I sub A. And what about the voltage dropped across the inductor? That's Eli, isn't it? That's Eli setting there. That's L di sub A dt. And then we have plus V sub B, which is our dependent voltage source. That's our KVL. We have minus V of t plus R sub A, I sub A, plus L sub A, di sub A dt, plus V sub B, and now we're back to where we started. I'll try to label some of these terms. That's the applied voltage. R sub A was the resistance in the armature circuit, or the armature resistance. I sub A is the current in that armature circuit, or the armature current. L sub A is the armature inductance. And V sub B is what's called the back electromotive force. Or if you're texting this, you might just say the back EMF. You might need to do that tonight as a part of your block diagram exchange. You guys have too much fun. And that's a time domain equation. Let's look at the back electromotive force a little bit more carefully, or just show the pieces that make it up. V sub B, I said it was a dependent voltage source. V sub B is actually proportional to the velocity of the motor shaft, which I'm labeling as omega. This K sub B is the back EMF proportionality constant. And omega is the angular velocity of the rotor shaft of the motor. And we can relate that to the position of that shaft. It's just the derivative of the motor shaft. Oh, let me go ahead and make one connection with this, and that is that you might see two different constants floating around, K sub B and K sub M. Those are actually equivalent as shown in the textbook, and so this, if you see this, you could just refer to that as the motor constant, meaning the faster the shaft spins, then the proportionality constant, K sub M, will then influence the voltage V sub B, which, if you look at this circuit, and let's say that we apply a constant voltage to that motor, and we're trying to get it to spin up, and let's say that the motor shaft is not spinning yet, then what's V sub B? If the shaft is not spinning, and V sub B is K times omega, and omega is 0, V sub B is 0, isn't it? So now we have 0 on that dependent voltage source, and we have a much larger current until that shaft gets to spinning. Then V sub B grows, and I sub A actually starts to shrink. So when you turn on a motor, it demands a lot of current. And if you play with motors, you've seen that or you've experienced that, and this sort of plays or illustrates one way of understanding how that might be happening. And that's all because of this back electromotive force. And our equations, then, that we're using are that the angular velocity of the shaft is just the time rate of change of the position of the shaft, and we're using the fact that the back electromotive force, K sub B, is equivalent to the motor constant K sub M. And the explanation for that can be found on page 75. And if I now make that connection, because V sub B is just sort of a new variable, but if I replace that with K sub M theta prime, then I just have I's, V's, and thetas in my equation. Yes? Yes, so now this equation is more than just electrical, isn't it? We now have derivatives of our armature current, the applied voltage V, and also in that equation is the angular velocity of the motor shaft, theta sub prime. That's one expression describing the dynamic relationship between the applied voltage and the shaft's output angle. But we also want to keep track of, or we need to keep track of, what's happening on the mechanical side. Because that theta is not just an arbitrary angle or position, it's influenced by the mass, the rotational inertia, and let's say any rotational springs or damping that might be on that shaft. And there's the load of the motor, which we have already identified an angle for that, which we called theta, and we also identified if we have current going through the armature, that current will actually introduce a torque on that load, on that motor load. Now, if we think, here's what I want us to be considering. This torque, motor torque, tau sub m, is analogous to force that we've been playing with in these translational mechanical systems. Now, instead of worrying about masses going horizontally or vertically, now we're worrying about rotational inertia spinning or rotating. Now, if I have a torque similar to, or if I just move this shaft in the direction of theta, what would happen to that rotational inertia, similar to if I pushed a mass horizontally? It's going to have some kind of inertia that opposes that movement, isn't it? That's our rotational inertia, or inertial torque, so let me call that, to be consistent with how we were doing it before, tau sub I. It will try to oppose that, and let's just say that there's maybe some fluid, or maybe that fluid is air, but there's some kind of damping that's proportional to the velocity of that shaft spinning, and that produces a torque, and we'll call that tau sub B. And to find the mechanical equations, like we did in the translational, we just need, in the translational, we sum the forces and set those to 0. Now that we're accounting for the inertial torque, we can do the same thing with torques. We can say, let's sum the torques and set those equal to 0. And looking at that collection of arrows, hopefully you can see that they're going in different directions. I now just algebraically sum those. So the mechanical torque, or the motor torque, tau sub m, is going in one way, and that's opposed by the other torques, which are tau sub I and tau sub B. This is the motor torque. This is the inertial torque. That's how difficult it is to spin that inertia. And here I'm going to call this is the rotational damping torque. So now if you were in a swimming pool and trying to move something in a circular manner versus if you were just out in the air, it's a little bit more difficult, isn't it, if you had some damping or more fluid around you? So that's what you can sort of think of with this rotational damping torque. That's going to depend on what we have access to or what we're living in terms of a system. And what we need to realize or understand is that this motor torque is actually proportional to the current in our armature circuit. So the more current we have flowing, the more torque we're applying to the motor shaft. This is our motor constant. And I sub A is the armature current. So this is just saying that our motor torque is proportional to the armature current. And this motor constant, what are the dimensions of that motor constant? What's torque? Do you remember what the units on torque are? It's kind of related to that storm we had this week. One of the pieces. Newton meters. Newton meters per ampere. So the motor torque has units, Newton meters per ampere. So that when you scale it by the current in the armature, amperes, you're going to get torque, which is Newton meters. Now, let's look at what else we have. How did we model translational inertia, or the force due to the inertia? F sub I, what was that? Mass times acceleration. So what would you guess the tau sub I, the inertial torque, might look like? The rotational inertia of that load times angular acceleration. So tau sub I, to describe that, that's going to be J times theta double prime, or that's J alpha, where this J, now we're getting into some physics. This is our rotational inertia. Hopefully you remember that from some physics class, maybe. And this is the angular acceleration, which is just the second derivative of the motor shaft. So here I'm saying that alpha of t is the time rate of change of the angular rotation, which is the second derivative of the shaft angle or position differentiated twice. And one more piece that we need to know in this formula, we have tau sub m, that's k sub m I sub a, that's in terms of variables we need, our current in the armature. Tau sub I, that's j theta double prime, and tau sub b, since that's dependent on the velocity of the motor shaft, or the angular velocity, then tau sub b is this b theta prime. Using those relationships now allows us to obtain our motor torque, which was k sub m I sub a, equaling our inertial torque, j theta double prime, plus the rotational damping torque, tau sub b, which is b theta prime. And we want a transfer function, so let's now move out of the time domain. This is a time domain relationship that is describing the mechanical side of this electromechanical system. If we Laplace transform the mechanical side, what happens to that time domain equation? That's what LTMS means if you're texting. LTMS. Laplace transform the mechanical side. That's usually in most of the text that you read, isn't it? LTMS. What happens if we Laplace transform that time domain equation? What happens to k sub m? It's a constant. That one's easy. What if we Laplace transform I sub a? It's I sub a. Did you understand the difference? I sub a was lowercase. I sub a was capital. And we're finished with the left-hand side. Now what do we do if we Laplace transform theta double prime? S squared. So we now have S squared j theta of s plus S b theta of s. And we want to find a transfer function in terms of voltage, V, and shaft angle theta. This I sub a is this intermediate variable. We want to get rid of it. And we had an I sub a in our electrical side. But now we can solve this second equation in terms of I sub a. I sub a of s is now S squared j over k sub m plus S b over k sub m theta of s. And if we have LTMS, what's LTES? Laplace transform of the electrical side. Here's our electrical side we want to Laplace transform. So that will just be minus capital V of S plus R sub A capital I sub S plus S L sub A I sub A of S plus S K sub M theta of S. And if we put V of S on one side, then it will now become positive, and we now have R sub A plus S L sub A I sub A of S plus S K sub M theta of s. And what I want to do is replace this I sub a with that expression in terms of theta of s. Doing that, I now have an equation v of s is equal to r sub a plus s L sub a times s squared j over k sub m plus s b over k sub m theta of s plus s k sub m theta of s. And are you getting as excited as I am? And the answer is yes. What do I have? I now have one equation that has two unknowns that I really need in that one equation. The shaft angle, theta, and the applied voltage, V, at the armature. And I can now find my transfer function from that. To clean this up, let me get rid of that k sub m in the denominator by multiplying both sides by k sub m. I now have k sub m v of s is equal to r sub a plus s L sub a times s squared j plus s b plus s k sub m squared, and all of that's times theta of s. And if you're really paying attention, you might see that there's a common s in all of those terms that I can factor out. So let me factor one of those s's out. And I'm now left with r sub a plus s L sub a, s j plus b plus k sub m squared. And now I can simply divide out to find my transfer function. My input was V, my output was theta. I'm now looking to find theta sub s over V of s. Or I now have k sub m over s times the quantity s L sub a plus r sub a times s j plus b plus k sub m squared. And if you're playing along at home, you've already seen that this is row 6 in table, whatever table it was, on page 77. I think it's table 2.4 in the 13th edition. What's the order of that system? If you multiplied that denominator, what would be the highest power of S? It'd be 3. So we have a third order system. And what do we have going on here? We have an electromechanical system, an electrical piece and a mechanical piece. And which piece is usually faster? Electrical or mechanical? Electrical's always faster, isn't it? I had to present, but I presented first yesterday, but ahead of mechanical. So we were way ahead of mechanical. But electrical happens on a much quicker time scale, doesn't it? But where's the mechanical piece in this transfer function? Right there. Sj plus b, isn't it? Where's your electrical piece? Right there. So let's identify some of these time constants, these speeds of the two different pieces of our system, an electrical piece and a mechanical piece that goes very, very slow compared to the electrical. Let's look at the mechanical time constant. And I apologize to those, well, actually, you're probably grateful that you're not having to see this demonstration of fast and slow in real time. But the mechanical time constant is going to be found from this mechanical factor. Meaning, let's factor out the B, and we now have S J over B plus 1. Or, do you see that that's, if you remember your Bode plots, we had to put factors into time constant form. And that meant we needed to make our constant always 1. And now we've made our constant term in this expression 1, and what was scaling S was our time constant, and that's J over B. Because what are the units on S? S is a frequency domain variable. What would you sort of associate the units of S being? Radians per second. It's per second, isn't it? So now something times per second, the units on that something to be dimensionless needs to be seconds. So this is really just S tau sub m plus 1. So our mechanical time constant is J over B. And we can do the same thing with the electrical side. The electrical factor is right there. So that if we factor out the resistance, we have S, L sub A over R sub A plus 1, or this is now R sub A, S tau sub E plus 1. Or the electrical time constant is L over R. Does that sound familiar? L over R being a time constant. Let's just pick some numbers, just illustrate what we might have in terms of relationships between these speeds. Suppose that I assign the inductance in my armature circuit to be 1 millihenry, 0.001. And let's just assume that the resistance is 1 ohm. Yes? Oh, yes. Good catch. So the question was, Tharp, you're using too many, you're overloading tau sub m. So let me say this is MECH. How's that? That's not the same as the motor torque. I was hoping you'd forgotten about that tau sub m. You guys just have too good a memory. But this tau sub m is the mechanical time constant, which is not the same as the motor torque tau sub m. Thank you for catching that. Is that clear? Hope that didn't confuse everyone. Didn't confuse me because I'd already forgotten what tau m was 10 minutes ago. It's now the mechanical time constant. All right. Now, what's the mechanical time constant? That's J over B. Let's just put some numbers in here. Let's say that our rotational inertia is 0.5 and B is 1, so that now this is 0.5 seconds. And if we needed to look at this ratio of mechanical time constant to electrical, we now have 1,000 times 1/2, or 500. So the electrical is 500 times faster than the mechanical, right? So what that allows us to do is essentially neglect the electrical dynamics in some instances. We may not even need to worry about it. And if we do, that lowers our order of the system to now second order. So I may fill in a little bit more notes, but just be aware that sometimes you can neglect the electrical dynamics because they happen in a blink of an eye relative to the mechanical dynamics. We'll pick up at that point on Monday.